are two kinds of averages in calculus. You learned one when we were doing derivatives. And now there's another one for us to learn as we do antiderivatives. So let's talk about the averages of derivatives and the averages of integrals as well. When you are working with derivatives, it was called average rate. Okay. The definition back in first semester when we want average rate is f of b minus f of a over b minus a. Okay, that's just simple. If you want to do the average distance, then you do the difference of the distances over b minus a. If you want the average velocity, you do the velocity of b minus the velocity of a over b minus a. It's always, that's the definition of average. When we get to antiderivatives, where our new definition is something called an average value. And they'll specify, find the average value. So you just need to know which average they're talking about. And the average value is found with the integral from the a to b interval as well of the function f of x in parentheses dx over the same difference b minus a. To help us remember that, we call this integral over interval. You'll hear students who have taken calculus before say, well, what's the definition of average value? Oh, integral over interval. Yep. Okay, and then that's always going to help you remember that's what average value definition is. Now that's the definition of it, but what is the average value? Okay, so let me help you visually try and understand what that is. Okay, the average value is the average of all the heights in a function over a certain interval. So it would be like if we drew a picture and we made super, super skinny rectangles. All of them were like one sliver wide, and we found all the heights of every single rectangle, and we averaged them all together. That's what the average value would be. So if you're thinking visually, okay, if you had a function, all right, let's just say, okay, some random function going from a to b, and you found every single individual skinny, microscopically fine, thin height, and you added them all up and then averaged them all together, that's what you would get. Okay, so etc. But this is what I like to think of it as. Imagine that this same graph is a tank filled with water. Can you imagine that this is like a fish tank or something, and there you shake the fish tank and all the water is wavy in there. All right. The average value is what would that same fish tank look like when all the water settles? Okay, because in the first one, when you have the waves, you have some parts of the water that are high and some parts of the water that are low. But if the water became smooth and calm, what would it look like? Okay, so going from A to B, and I'll just make it look like it's a tank or something. Okay, the water might settle like right here. And the value that it settles at, so it's not high, it's not low, it's just constant now, this is called the average value. So visually, that's what you're looking for. If you were to level out a function and make all the highs and all the lows equal to each other, what would the function, and it basically make it a rectangle, where would that line have to be? Okay, and that is called the average value right there, whatever that y value is. Okay, so let's practice that. All right, so find the average value on the interval from 0 to 4. Oops, closed interval, sorry. There we go. For the function e to the x. So visually, e to the x on 0 to 4 looks like this. Crosses through and then heads up. So we've got 1, 2, 3, 4. One big wave. If we were to take that and make an equivalent rectangle, what would the height of that rectangle be? All right, so visually we want to find there's some rectangle here that's partially above and partially below, and that partially above and that partially below are perfectly equal to each other and would all level out exactly right. Where is that going to be? And so we use the definition. Average value is the integral from 0 to 4 e to the x function dx over the interval 4 minus 0. So it's integral set up over the closed bounds and then over the interval. Okay, so we hopefully understand the geometry of it, but now we want to work the calculus. And so the antiderivative of e to the x is e to the x itself divided by the natural log of e plus c from 0 to 4 over the interval 4 minus 0. And then you're just going to work this like you were working yesterday. So the natural log of e is 1, and so I'll have e to the 4th plus c minus e to the 0 minus c all over the value of 4. Now the c's do cancel each other out, but again, e to the 0 isn't 0. E to the 0 is 1. And so I'll have e to the 4th from the first quantity minus 1 from the second quantity over 4. Okay, that is the exact numerical value of the average value of this function. Now that's going to turn out to be an irrational number of some decimal value. We could figure out what that is, whatever e to the 4th minus 1 over 4 is. That would be where you could draw a perfectly horizontal line, and so this is happening at e to the 4th minus 1 over 4. That value right there with a base of 4 creates a perfect rectangle that has area exactly equal to the area under the yellow curve. So this area here is exactly equal to this area here. I'm not saying I drew it to scale, but okay, that those area pieces exactly are equivalent to each other. Now sometimes the equation that you're given is not, this is a good verb, is not integrable. That means it's not something you can take the antiderivative of yet. You haven't learned enough to be able to do it. So you might need a Math 9 to help you out with that, and then you'll be coming up with an irrational number. So maybe something like find the average value. Okay, on the interval from 1 to 7. for the function, the natural log of x. All right, so visually, the natural log of x comes up and crosses the x-axis at 1, and then heads off that direction. So there's 1, 2, 3, 4, 5, 6, 7. And so we're looking visually for that area right there. So somewhere there is an average value, question mark, we don't know where it is, but at some point there is an average value where the rectangular height would be exactly equivalent to that. And so we set this up the same way. The average value is set up as the integral from 1 to 7 of the function, the natural log of x dx, over the interval 7 minus 1. Now you don't know how to do the antiderivative of the natural log of x yet, because the natural log of x is not anyone's derivative. There was no derivative that made the natural log of x perfectly yet. And so this would be an opportunity for you to have to rely on your calculator. So go ahead and get it out and do a Math 9 and estimate the value on that Math 9. So we know the denominator is going to be 6. Okay. That we now know that this would be a height of 1.270. That would be the average height or the average value across that interval from 1 to 7 that would create a rectangle with equal height to the logarithm area. Okay, any questions about that so far? All right, now you can work backwards to find that number also using your calculator. All right, so here's an example of how we would work backwards. Okay, when would you achieve half the area under that integral? Let's go back to the original one we were doing, 0 to 4 e to the x dx. All right, when would you get to half of the area? That you would, if you have the amount of area from 0 to 4, how do you get halfway? All right, one multiple choice option might be this, that somebody would just say, oh, just go to 0 to 2 then. 0 to 2, that would be a multiple choice answer. If you go from 0 to 2, that's halfway, and then you'll get half the area. And you'll get half of 0 to 4. Right, that is faulty thinking. It's faulty reasoning. That is not true. Just because you go halfway on the x-axis doesn't mean the area underneath is going to be half of what you started with. Why is that faulty? Not a constant, right? It's, the e to the x is a curve, it's curved. And so this is not a true statement, and so that's not going to work. Okay, so how do we use our calculators to do this? Well, first we got to know how much area is under 0 to 4 e to the x dx. All right, we've already done that. We know that that's going to be e to the 4th minus e to the 0, which is e to the 4th minus 1. But I would like to know what the numerical value of that is. All right, so I'll figure that out a second. So e to the 4th minus 1 comes out to be 53.598. So our question is 0 to something, and we don't know what that something is. And so we're going to call it k. It's not 2, I can tell you that. Okay, it's not going to be 2. So 0 to something needs to get me halfway to 53.598. And our calculator can solve that for us. So let me show you how to do that. And so to confirm, we have that 0 to k of e to the x dx did turn out to be half of what we were expecting, 26.798.